Welcome to a Riemann sum example with a right-hand rule. So in this example, we're going to use Riemann sums to approximate the definite integral from 1 to 3 of x squared minus 2 dx. This time around using the right-hand rule with n rectangles. So again, the idea here, we have our graph. And we are looking at the integral from 1 to 3. And we want to break into a bunch of rectangles. So again, we have our total width. Is 3 minus 1 or 2. And we're going to split that width over n rectangles. And so we have, once again, 2 over n for each of our rectangles in width. We are going to use the right side of the rectangle to determine height. So again, the height of each rectangle is based off the right side. Okay. So our first rectangle will go from x equals 1 to x equals 1 plus 2 over n. And we want to use the right side. And so the height will be based off of this right side. So our height will be f of 1 plus 2 over n using the right side. So once again, when we figured out our total width, the 1 came from the lower bound of our definite integral. 3 came from the upper bound of our definite integral. We were splitting over n rectangles, hence our 2 over n. And then this 2 over n is going to serve as our width of each individual rectangle. So the first one goes from 1 to 1 plus 2 over n. So we have our height of the rectangle is f of 1 plus 2 over n, which in this case would be 1 plus 2 over n squared and then minus 2. And the width is 2 over n, so the area would be a width of 2 over n times our 1 plus 2 over n squared minus 2. So this should look similar to what we did in the previous lecture video. But again, we're using that right side, so we're starting with a 1 plus 2 over n. Now, if we want to look at the ith rectangle, rectangle number I, we're going to go from x equals 1 plus, we're going to add on a bunch of copies of 2 over n. And once again, we're adding on I minus 1 copies of 2 over n. So the first rectangle, we want to add 0 copies of 2 over n, hence doing I minus 1. And then each one we add an additional 2 over n. We're going to go from that value of x to x equals 1 plus I copies of 2 over n. since we want the right side, our height will be based off of this x equals 1 plus I over 2 times n. So the height will be f of 1 plus I times 2 over n, or this 1 plus, I'm going to reverse this and write it as 2 over n I squared minus 2. So this is the height of the ith rectangle. Again, the width is just that 2 over n. So we have the area will be 2 over n times 1 plus 2 over n times I squared minus 2. From here, we can go ahead and do our approximation for the definite integral from 1 to 3 of x squared minus 2 dx. So this should be approximately the sum of our n rectangles, letting I run from 1 to n. And then the area of each of those rectangles is 2 over n times 1 plus 2 over n times I squared minus 2. So from here, we can go ahead and solve. So I'm going to pull the 2 over n out front. It doesn't involve an I. We can pull it out front. We have I equals 1 to n. Then we can go ahead and multiply out 1 plus 2 over ni, the whole thing squared. This becomes 1 plus 4 over ni plus 4 over n squared, I squared, and then minus 2. Otherwise known as 2 over n times the sum from I equals 1 to n of negative 1 plus 4 over ni plus 4 over n squared I squared. This sum we know how to take. So the first piece, we're just looking at the sum of I equals 1 to n of negative 1. Then we have 4 over n times the sum from I equals 1 to n of I. And then we're adding 4 over n squared times the sum from I equals 1 to n of I squared. So this becomes 2 over n times, in brackets, we will have a negative 1 times n, or a negative n. Then we have a plus 4 over n, and the sum from I equals 1 to n of I is n times n plus 1 over 2. Then we have plus 4 over n squared. And the sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1, that whole thing over 6. So this is what we wind up getting. I haven't simplified at this point. We could go ahead and simplify. If we multiply in that 2 over n, we wind up with negative 2 plus 4 times n plus 1 all over n. And then we'd have plus 4 times n plus 1 times 2n plus 1 all over 3 times n squared. We would have had 8/3, and then I canceled out or sorry, 8/6, and then I cancel out 2. So this was using the right-hand rule. Again, our sums were a little less complicated this time around because the right-hand rule, we don't have to worry about using that I-1. We just get to use that times I. And therefore it makes our arithmetic a little more pleasant. So from here, if we do our general formula for the right-hand rule, so for our general formula, if we have to approximate the definite integral from a to b of f of x dx using a Riemann sum with n rectangles. Using the right-hand rule, we have that our ith rectangle will have width equal to, we do the total width, b minus a, split over our n rectangles. X will go from x equals a plus I-1 times this b minus a over n to x equals a plus I times b minus a over n. We are going to use this right hand x, so our height will be f of a plus I times b minus a over n. The area will be that width, b minus a over n, times f of a plus I times b minus a over n. And then our approximation for the definite integral from a to b of f of x dx will be given by, we take the summation from I equals 1 to n over all of those rectangle areas. So we have b minus a over n times f of a plus I times b minus a over n. Or we can go ahead and pull out b minus a over n. Every single term has that same factor. And then times the sum from I equals 1 to n of f of a plus I times b minus a over n. So this is the generic formula that we have at the end here. So you are welcome to jump straight to this generic formula. You don't have to walk your way through the little bit I did for the ith rectangle here. If you're comfortable with it, you can go straight to this formula. If you're not, you can work your way through the ith rectangle. So this is a way we can go ahead and approximate using the right-hand rule. Again, I find the right-hand rule more pleasant than the left-hand rule, just in terms of the formula we wind up working with.